Okay, now we're going to talk about energy, rate, and equilibrium. So now we're getting to a little bit more complex concepts. Thermodynamics, the study of energy, work, and heat. Okay, we apply it to chemical change, like I said before. Calculate the quantity, in a chemical equation, we either gain or lose heat, exothermic, endothermic reactions. So in a chemical change, we can calculate the quantity of heat obtained from combustions of 1 gallon of fuel oil. So you can actually, if you buy a furnace or a gas grill, it's actually calculated for you. You'll say the gas grill produces 20,000 BTU. That stands for British thermal units. It's a measure of the energy that's coming out. We can apply it to physical change, determine the energy released by boiling water. Okay? So the laws of thermodynamics help us to understand why some chemical reactions occur and others don't. Just because you mix A and B together doesn't mean you're going to get a product. So going back to our kinetic molecular theory, molecules and atoms in a reaction mixture are in constant random motion. So they frequently collide with each other. But you have to collide each other with sufficient energy to break the bonds, because the chemical reaction is you're breaking bonds into reactants and reassembling them into products. So if they just bump into each other and they don't break the bonds, nothing happens. The absolute value for energy stored in a chemical system cannot be measured. What we can measure is the change in energy during these chemical changes. So a system is identified as containing the process under study. The surroundings is the rest of the universe. So let me see if I get the pen working here. Black, pen, this, pen, this. So here I have a room with a furnace in it. The furnace is producing heat. Our system would be the room. Everything outside the room is the surroundings. So if I open the door, the heat goes out the door. So you remember when you were small, you'd open up the door, your dad would yell, "Close the door, I'm not heating up the rest of the world." Essentially, he was right. You are heating up the rest of the world because now you're opening up your system to the surroundings. So energy can be lost from the system to the surroundings, or it can be gained at the expense of the surroundings. So here we have again the room, heat's coming out to the surroundings, or we can bring heat back into the system. So then the room loses the surroundings. So if you think about how your heat pump works, if you have a heat pump in your house, into winter, it's blowing heat into your room. Where's the heat coming from? The heat fairy. No, it's coming from outside. It's taking the heat from outside and transferring it into your house. In the wintertime. In the summertime, it runs in the other direction. It's removing the heat from your room and venting it outside. What, outside? There's still heat out there. Believe it or not, there is heat outside, even if it's cold. There is amount of energy outside. And a heat pump will work down to about -10. or actually about 10 degrees. And then after that, it kicks on the energy reserve. Sometimes if you have an older one, a little light will light up, which means now you have electric heat. And if you watch your little heat meter, it's going like this, and the energy starts spinning like crazy because now you're making Duke Energy a lot of money. The first law of thermodynamics, energy of the universe is constant. So all the energy in the universe, once it was created, that's it. It's also called the law of conservation of energy. So where does the reaction energy come from that is released, and where does the energy go when it's absorbed? Good question. Here we have a reaction. We have molecule AB reacts with molecule CD. They give us two new products, AD and CB. So you can see the bonds there. Each chemical bond is stored chemical energy. So if the reaction is to occur, you have to break first the A, B, and CD bonds, and that requires energy. So you have to put energy in. When you form the AD and CB bonds, you release energy. So if the energy required to break the bonds is less than the energy released when the bonds are formed, there's a net release of energy. You have energy left over. You will produce heat. That's called an exothermic reaction. Exo meaning outside, thermic obviously meaning heat. There's lots of examples of that. I mean, firecrackers, dynamite, obviously, when that reaction occurs, it releases heat. Meals ready to eat for people that are in the military. You mix the water and the chemicals are in there. There's a reaction that occurs, releases heat. That's what heats the food. If the energy required to break the bonds is larger than the energy released when the bonds are formed, you have to supply some more energy to keep it going. That's called an endothermic reaction. So there's certain types of reactions, you have to get them going, you have to keep adding energy to keep them going. Otherwise, they'll stop. So here, and look at this diagram, this is the progress of the reaction. This is the enthalpy. Enthalpy is another term for energy. We'll talk about that in a little bit. So here we have a high energy in the reactants going to a low energy in the products. H is the symbol for enthalpy. So you see this delta H. To calculate the change in energy, it's the products minus the reactants. So here we have a low number minus a high number. We're going to get a negative number for delta H. So here we're taking methane, oxidizing it, burning it, essentially, natural gas furnace. We end up with carbon dioxide and water and leftover 211 kilocalories per heat. And that's the heat that heats your room. The bottom reaction here, the reactants are lower in energy than the products. So if we start off with ammonia gas, add 22 kilocalories of heat, we can break the ammonia bonds and end up with nitrogen and hydrogen. So enthalpy, like I said, represents heat energy. The change in enthalpy, delta H, is the energy difference between the products and the reactants. So the delta H of the reaction is the delta H of the products minus the delta H of the reactants. If energy is released, and it's an exothermic reaction, the sign of delta H will be negative, because the products are lower energy than the reactants. So you got a smaller number minus a bigger number, you're going to end up with a negative number. So the combustion of CH4, the delta H is minus 211 kilocalories. If energy absorbed, the delta H will be positive. So for the decomposition of ammonia, the delta H is plus 22 kilocalories. So here are the following processes, exothermic or endothermic. Fuel oil burned in a furnace, exo or endo. Why do you burn fuel oil in a furnace? To what? Produce heat. So if you're producing heat, what kind of reaction is it? Exothermic. The bottom one here, we have glucose going to ethanol and CO2. It's fermentation. The delta H is minus 16 kilocalories, exo or endo. That's also exo. It's a negative number, yes. So when glucose ferments, if you're making moonshine, ethanol, CO2, it will get warm. Spontaneous and non-spontaneous reactions. Most, but not all, exothermic reactions are spontaneous. You saw when I threw the sodium in the water, that went just like that, produced the heat and the foam. That was spontaneous. If I throw a log on a fireplace, does it spontaneously burst into flames? No. Even though it's an exothermic reaction, you got to do something first. So it's non-spontaneous. Most, but not all, endothermic reactions are non-spontaneous. So thermodynamics is used to help predict if a reaction will occur spontaneously. However, we need another factor called entropy. The symbol for entropy is S. And you may have heard the term entropy before. Entropy means a state of randomness. You know, the universe is said to be expanding, so it's increasing in entropy. It's becoming more random. The second law of thermodynamics, the universe spontaneously tends towards increasing disorder or randomness. So entropy, like I said, is a measure of the randomness of a chemical system. High entropy, highly disordered system, the absence of a regular repeating pattern. Low entropy, well-organized system such as a crystalline structure. So if you have crystalline sodium chloride, it's really highly organized, chlorine, sodium atoms, very low entropy. A gas, molecules are all over the frickin' place going around, that's high entropy system. There's no such thing as negative entropy. The change can be negative, but you can never have negative entropy. It's like having a concentration less than 0. You can never have a concentration less than 0. You can have 0. You can't have less than 0. I can't give you less than no money. So which has the greatest entropy, helium gas or sodium solid? The gas, because the molecules are random in motion and far apart and very disordered. H2O liquid or H2O gas? The gas. Again, because their molecules are farther apart, moving about randomly. Is that the only ones on there? Yeah. So again, we measure the change in entropy. is the entropy of the products minus the entropy of the reactants. A positive delta S means an increase in disorder for the reaction. A negative means a decrease in disorder for the reaction. We can go from very disordered to very ordered. If I freeze water, it goes from a liquid to a solid, the entropy change is negative. So if you look at these, melting, vaporization, and dissolution, all of these have positive delta S's. They're all becoming more random. Conversely, if you go in the other order, freezing, condensation, and, well, I don't know what the opposite of dissolution would be, precipitation, you're becoming more ordered. So you'd have a negative delta S. So, if we look at this, it's exothermic and positive S. So if I look at delta H and delta S, so if I have exothermic, what's the sign of delta H? Negative. Positive entropy, delta S would be positive. So those are spontaneous. If endothermic and negative delta S, so this is negative, this is positive, it's non-spontaneous. For other situations, and the other situations would be they're both positive or they're both negative. It depends on their relative sizes. And we'll see that coming up. So here we have this bulb where we have all the gas on one side. We open this stopcock and it diffuses to the other side. That's a spontaneous process. To get it from both sides to one side, that doesn't really occur easily. That's a non-spontaneous process. We need another term, free energy, delta G, because it used to stand for Gibbs free energy. That's where the G came from. Represents the combined contribution of enthalpy and entropy values for a chemical reaction. So free energy predicts if the reaction is going to be spontaneous. Delta G, and you see that super zero equals delta H super zero minus T delta S, where T is the temperature in Kelvin. So you could see if, we're going to put delta G over here. Looking at that equation, if delta H is negative, delta S is positive, the answer is always going to be negative. Because you're going to have negative minus a positive, which is always going to be negative. So delta G is always going to be negative. Delta H is positive, delta S is negative. You have a positive minus a negative, which will always give you a positive. Delta G is always going to be positive or non-spontaneous. For the other two, depending on what the temperature is, will determine whether it's spontaneous or non-spontaneous. Bless you. That was spontaneous. So what does that mean? So we have an ice cube. Room temperature right now is about 25 degrees Celsius, I think it is. So if I put the ice cube on the bench, what will happen to it? It'll melt. So that process is, it's becoming more random, so delta S is positive or negative. It's becoming more random, it's positive. Is it absorbing heat or giving off heat? Absorbing heat, so delta H is it's positive. Let me see. So positive, negative. It turns out at 25 degrees, it'll come out to be negative, so it'll be a spontaneous process. But if I lower the temperature, if I go take the ice cube and I'm in Antarctica, and I take it outside, is that going to be spontaneous or non-spontaneous? Non-spontaneous. Because the temperature is too low. So depending on the temperature, you can either have a spontaneous or non-spontaneous reaction. Didn't we just do that? We just did that. So you need to know both the delta H and delta S to predict the sign of delta G. So delta H is positive and delta S is minus. Delta G is always positive regardless of the temperature. Delta H is negative and delta S is positive. Delta G is always minus regardless of the temperature. Our ice cube, we had delta H positive, absorbing heat. Delta S positive, because it's becoming more random. Delta G sign depends on the temperature. At high enough temperatures, it's spontaneous. At low enough temperatures, it's non-spontaneous. And if they're both negative, it depends on the temperature too. So this is useful if you know this and you want a reaction to go. You're manufacturing something. You got to know whether you're going to heat it or not and what temperature. Or if you don't want it to go, what temperature to keep it below. So if you're making, let's say, a drug and you know it'll oxidize, i.e. decompose, at a certain temperature, you want to keep it below that temperature. That's why some of them have little directions on there, refrigerate. Some of them even freeze until you need to use it. How do we determine energy change? Calorimetry is the measure of heat energy changes in a reaction. So a calorimeter is a device which measures heat changes in calories. The change in temperature is used to measure the loss or gain of heat. And this is what they call a coffee cup calorimeter, because it's made out of 2 styrofoam coffee cups, which insulate the system from the surroundings, because styrofoam is an insulator. What you do is you put your reaction mixture in there and you measure the temperature change as the reaction occurs. And from knowing the concentration of the reactants, you can tell how much heat is gained or lost. So an exothermic reaction, the heat's released by the reaction, absorbed by the surrounding solution, the temperature goes up. The endothermic reaction, the temperature goes down. And I think not this week, but next week in lab we'll actually do some calorie measurements. People always like that because we burn stuff. The specific heat is the number of calories of heat need to raise the temperature of 1 gram of the substance 1 degree Celsius. Q, which is the heat gained or lost in a reaction, is equal to the mass of the substance times the change in the temperature of the substance times the specific heat of the substance. Specific heat of water is 1 calorie per gram per degree C. So if I take 1 milliliter of water at, let's say, 24 degrees C, that's 1 gram, because density of water is 1 gram per milliliter, heat it till it gets to be 25 degrees C, I've spent 1 calorie. So to determine the heat released or absorbed in a reaction, you need to know the specific heat, the mass of the solution in grams, and the temperature change, final minus initial. So here we have 1/10 of a mole HCl is mixed with 1/10 of a mole potassium hydroxide in a coffee cup calorimeter. The temperature of 1.50 times 10 to, or 150 grams of the solution, increases from 25 degrees C to 29.4 degrees C. The specific heat of the solution is 1 calorie per gram per degree C. Calculate the quantity of energy evolved. So the change in temperature is 29.4 minus 25, which is 4.4. That's your delta T. So Q is equal to the mass, 150 grams, times the temperature change, 4.4 degrees C, times 1.0 calories per gram per degree C. Turns out, if we do that, 6.6 times 10 to the 2 calories. So that's how much energy is released. So we can do that for a lot of reactions. So what you're going to do in lab not this coming week, but probably next week, you're going to have a certain amount of water in a beaker, say 100 mils, so we know that weighs 100 grams. And we're not using a coffee cup calorimeter. We're not using calorimeters. This is quick and dirty. We're going to take a food item, let's say like a Dorito, set it on fire, and while it burns, we're going to use the heat from it burning to heat the water. And from the temperature change, the mass of the water, you're going to figure out how much heat is released, and from the weight of the Dorito chip, that'll tell you how many calories per gram. Now remember, these are chemical calories, not food calories. Anybody remember the difference? How many? I'm sorry, what? Yeah, which one's bigger? Capital C, which is the food calorie. So there's 1,000 chemical calories in a food calorie. And what we'll do is do a bunch of foods. I think we do marshmallow, Dorito, butter popcorn.
So on the back of the label, when you read 280 calories, there's 280 food calories, right?
That's 280 food calories, 280,000 chemical calories. Which is why, like, you eat that Snickers bar, you got to run 40 minutes on the treadmill. Because that's a lot of calories to burn. Okay? And to lose 1 pound of fat, you have to burn essentially 3,500 calories, food calories, more than you take in. So we're really, I'm kind of digressing here, all that diet stuff, you read about this and that, it all comes down to you got to put out more calories than you take in, regardless of where they come from.
As far as weight is concerned.
Yeah.
Not as far as like arteries and stuff like that.
As far as your arteries and that?
Percent people still like damaged organs.
Oh yeah. You can, in terms of getting cholesterol and that, no, in terms of just losing weight and that. That's like if you drink Pepsi or Coke, It's like 170 calories per can. If you just switch to a diet drink or water, that's more than half a pound a week right there. So this reaction, since it was positive, it gave off heat. The reaction was exothermic. The question would be, what would the energy evolve for each mole of HCl reacted? Well, we had 1/10 of a mole in the reaction. So if it was 660 calories per 1/10 of a mole, it's 6,600 calories per mole. You would take it and divide it by the amount. So sometimes because this was generated by 1/10 of a mole of HCl, for a mole it would be 10 times the amount. Just like if you read your food packages and you say, okay, I'm going to eat this muffin, and you say, oh, it's 450 calories. Well, that's not too bad. But then you say serving size, 1/3 of a muffin. My God, who the hell eats 1/3 of a muffin? So that's 1,320 calories. The recommended allowance by whoever decides what the recommended allowance is 2,000 calories a day. So pretty much you ate half your allowance calories in that stupid muffin. Okay? I think we all should go out and run around the building. So again, the nutritional calorie is 1,000 little calories, the large C. And what they use what's called a bomb calorimeter, which has nothing to do with explosives. It's just that it's super insulated. And they have a known solution of a known weight of water in there, and so they put your sample in here and they ignite it, and they burn it, and then they measure the temperature change, and from that they know how many calories. So now if you get your Snickers bar, it's not like they burn a Snickers bar in there. They burn, what's in Snickers bar? They'll burn the almonds, and they know 10 grams of almonds releases so many calories. And they'll burn chocolate, and they'll burn whatever else, sugar. And then we look at the ingredients, you say, okay, there's 4 grams of almonds. They know how many calories per gram of almonds. They calculate how much the bar would be. So 1 gram of glucose is burned in a bomb calorimeter containing 1,250 grams of water. It went from 24.5 degrees to, and this should be 31.5 degrees C. Calculate the fuel value. Change in temperature was 31.5 minus 24.5, 6.1 degrees. The surroundings of the calorimeter is water with a specific heat capacity of 1 calorie per gram per degree C. And we go here. So we put what's in there. This was the weight of the water, temperature change, specific heat. The Q is 7.6 times 10 to the third calories, which is 7,600 calories, or 7.6 nutritional calories divided by 1,000. So 1 gram of glucose contains 7.6 nutritional calories. So if you're going to make a cake or something and you put glucose, I don't know why you put glucose in there, but they would do it with sucrose, which is table sugar. And if you put so many grams of sugar in there, you could calculate how many calories are in that cake. And if you slice it into 12 slices, you can figure out how much is in a slice. Okay, I think a little. So we talked about thermodynamics, heating something, whether it'll make it go, not go, spontaneous, non-spontaneous. Kinetics, on the other hand, will tell you how fast it goes. That could be very useful too. If you're going to make something that would explode, you'd kind of want to know how fast it's going to go so you can get out of the way. So thermodynamics determines if a reaction will occur spontaneously, but tells us nothing about the amount of time the reaction will take. Guess what? Rust is a spontaneous reaction. It is also exothermic. It gives off heat. Normally we don't feel it. If you got iron railings in that are rusty, it doesn't feel warm or that. But if you take real fine particles of iron or magnesium, and those are these buy and fix and that have a little patch on it, and you peel off the patch, the air gets in there, a lot of surface area, rusts real fast, and it generates heat. Exothermic. Now, rust is not something that, it's a surface reaction, doesn't take place real fast. It's not like you stick a piece of metal out and the next day you come in and it's rusty. It could take months or years or that. But it's spontaneous, but it's not fast. Throwing sodium in water is spontaneous and fast. So kinetics is the study of the rate or speed of a chemical reaction. It also tells us, gives an indication of the mechanism, step-by-step descriptions of how reactants become products. And that's something that's used a lot, so we know how you go from A to E. Do you go from A to B to C to D to E, or do you go from A to B to D to C to E? Kinetic information represents changes over time. So here we have A is the reactant, B is the product. You can see over time the number of A molecules decreases. At the same time, the number of B molecules increases, because obviously A is going to B. And this is just a graphical not a graphical, a pictorial representation. We see the purple molecules are going to the green ones over time. So we actually see a color change. And if you have an instrument that measures color, you can follow the progress of the reaction and determine how green it's becoming. So here we see this is an actual reaction. It starts off orange, and as it goes closer and closer to completion, it becomes clear. So if we stick this in what's called a spectrophotometer and look at the absorbance of the orange color, we're going to see over time it's going to decrease. So those values are going to go down. Then we can do some math and figure out what rate it's going down at, which will tell us how fast it's going. So here again, we're burning methane. To do that, we must break the carbon-hydrogen bonds and the oxygen-oxygen double bonds. We have to form the carbon-oxygen double bonds and the OH bonds. So we require energy to break the bonds, so that comes from the collision. And it has to have sufficient energy to break the atoms. And it has to be effective collision. It's one that produces product molecules and leads to a chemical reaction. What does that mean? That means they have to hit in the right orientation. If I blindfold you and say, okay, You have to come together and shake hands with somebody. You have to come up essentially face to face. But if you're blindfolded, you can't see that. So you may come up somebody from behind, so you can't shake hands. So even though you may collide, it's not effective. So you got to have the right orientation. Activation energies, the minimum amount of energy required to initiate a chemical reaction. So we have to look at potential energy during the reaction. An activated complex, an extremely unstable, short-lived intermediate complex. Formation of this activated complex requires energy to overcome the energy barrier to start the reaction. What does that mean? Let's go back to our fire log in the fireplace. Well, it just doesn't spontaneously ignite. We know eventually when it burns, it's going to give off heat, so it's exothermic. So what do we got to do to the log? To start a fire, what do you got to do to the log? You got to heat it, right? You put kindling in there, newspaper or whatever, you set that on fire. That fire eventually starts the log on fire. So we're adding energy. Okay? Once we get the log burning, do we have to do anything? No. Well, I mean, we don't maintain it, but I mean the log, assuming it'll burn completely. So we don't have to, and it releases energy. Fortunately, it releases more energy than we spent. So if we kind of look at this, if I look at my delta H, my energy, and the reaction goes this way, I'm starting here at some point. Here's my log or my reactant. I'm adding energy, right? So delta H is going to do what? Go up, right? So I'm going up. Oh. I'm going up. There comes a point where I reach this activated complex. Extremely unstable. So I reach the top. Now the log is lit. And when the log is lit, it's going to release energy, so the delta H is going to go down. And since it releases more energy than it took in, our product is going to be lower energy because for an exothermic reaction, delta H is what sign? Negative. So the energy we put in from here to here is the energy of activation, E sub A. That's the amount of energy we need to put in to overcome a state. And there at the top is our activated complex. So if you kind of look at that diagram, it kind of looks like a what? Theme park, roller coaster. So if you've ever been on an old-fashioned roller coaster, a wooden one, right? You get on it, clickety-clack all the way up. Something's towing you up to the top, so you're expending energy. Once you get to the top and get over that hump, nothing's holding on to you except the track, and you're plummeting down. So due to gravity. So that's all the energy you're releasing. And you're probably releasing more energy than it took to get to the top, because usually when you come roaring into that station, they have to put a little brake on to stop you. So that's exactly what I drew. So that activated complex can't be isolated from the reaction mixture. You can't go in that log and stop it at the exact moment it starts on fire. Because once it gets going, it just goes. So exothermic, the energy of our products is lower than our energy of the reactants. Endothermic, we have a much larger activation energy, so it takes a lot of energy to get it going. And then once we get going, it doesn't release a lot of energy, so we have to keep providing more energy to it. The energy of the products is greater than that of the reactants. So you could think of something like, pardon? Refrigerator is not really a reaction. I'm thinking more like cooking, baking a cake. You can't just stick it in the oven and then turn the oven off. It'll stop cooking. Because that's an endothermic reaction. Or let's say you're going to make, okay, Thanksgiving turkey. Turkey usually cooked in about 3-4 hours. So you got the oven 350, right? Preheat it. Take the turkey, put it in, turn the oven off. Come back in 3 hours. Ain't going to work. Because it's going to stop cooking. You have to keep providing that energy. Take the turkey out of the oven, you provide it the energy, you drop the turkey, the pan spills, the grease catches on fire, set your house on fire. You walk away, you come back in 3 hours. Fire didn't stop, it just kept going, so that's an exothermic reaction. You won't stop till you have no house. Okay. Maybe not the best of examples, but. What? Huh? Happens every year, especially with those fried turkeys. Yeah. What factors affect reaction rate? Structure of the reacting species. Molecular shape and orientation, concentration, temperature, and physical state of the reactants. How so? Let's see. Oppositely charged species react more rapidly. Why? To have a reaction, the molecules have to do what? A collide, right? So if I just have neutral molecules, but if I have one that's positive and one negative, isn't it more likely to come together? So associated ions in solution whose bonds are already broken have very low activation energy. You don't have to drive them together. They're attracting each other to begin with. Ions with the same charge do not react because like charges repel. And bond strength plays a role. Covalent molecule bonds must be broken with the activation energy before new bonds can be formed. The magnitude of the activation energy is related to bond strength. So again, what type of covalent bonds are there? There's 3. Not intermolecular attractions, bonds. You have the single bond, single, double, and triple. Which one takes most energy to break? The triple bond. Yeah, so it's like think of a piece of wood, 3 pieces of wood as opposed to 1 piece of wood. It's harder to break. So the activation energy of that, if you have to break that, is a lot higher than breaking a single bond. Molecular shape and orientation. Large molecules may obstruct the reactive part of the molecule. And only molecular collisions with the correct orientation can lead to product formation. So For the second one, let's say I have AB plus C goes to C B plus A, which means C replaces A. So remember, these things are rotating in space. So if C hits B, nothing happens. C has to hit A for something to happen. So that's what I mean about orientation. What about shape? Okay, if I have a molecule and I want to hit that Br with something, that's not too hard. Hit that bromine, it's just sticking out there. But if I have a shape like this where I have all these other atoms around the top and bottom, I'm kind of shielding that Br. It's going to be a lot harder to react with that one. It's something called steric hindrance, which means I'm blocking it. I can't get in to react with it. Concentration. Why does that affect the rate? As the concentration increases, the rate increases. Why? More chances, more collisions. Right? If there's just 4 of you in this room and I blindfolded you and you say you had to find each other, it would take, bump into each other. It would take a while. If I had 200 of you in here blindfolded, it wouldn't take you long to hit somebody. So you have more reactant molecules per unit volume, more collisions per unit time. It goes faster. Okay? Temperature. Rate increases as temperature increases. Why? Besides reading that. The particles move what when you heat them? Faster. If they move faster and they hit, remember, not only do they have to hit with enough force to break the bonds. So the faster they're moving, the more of them are going to break bonds. So the higher kinetic energy means a higher percentage of these collisions will result in product formation. The physical state. All right, if you look at the solid state, atoms, ions, compounds are close together but restricted in motion. So it's very difficult, okay, if how come we got 2 mice? I have this, if this was a single block, it's very difficult for me to react on the atoms inside the block. I can't get to them. I can only react with the atoms on the surface. Okay? Rusting is a surface phenomenon. Okay? It just occurs on the surface. It takes a long time for it to rust through. So you ever watch American Pickers and they're out somewhere in the middle of podunk somewhere and they find an old bicycle or something in the weeds that have been there for 40 years. Oh, we can clean that up. Yeah, it's just surface rust. Sometimes it rusts all the way through. But gaseous state, oh, particles are free to move, but in the gas, what about the particles? They're free to move and they're moving around crazy, but when we say gas, they're far away. Gas is mostly empty space. So the odds of them hitting each other, it's pretty much slim to none. It's pretty good. Slim to none is pretty good. It's pretty far apart. The liquid state, particles are free to move and are in close proximity. So most of the reactions we do are in liquid state. A catalyst, that is substance that increases the reaction rate. It doesn't take part in a reaction. Okay? It undergoes no net change. Doesn't alter the final product. It interacts with the reactants to create an alternative pathway for product production. So here's, let me get this down a little bit. Uncatalyzed reaction, you see this big activation energy. Same reaction, same product, reactants and products, catalyzed, a lower activation energy. Give an example again, okay, I'm going to blindfold everybody in here. The object is to get out that door. That would be the product. And it would take you a while for everybody stumbling over each other to get out the door. Okay, now I take one person, remove their blindfold. They're the catalyst. What's that person going to do? They're going to grab everybody, pull them over to the door, and throw them out, okay? The product, the end result's still the same. It happens much faster. Where do we have catalysts? In where? Catalysts, where? Come on, you guys all have them. 2 spots.
On those boiling chips catalysts?
No. No, I'm talking about every day. How'd you guys get here today? Yeah. Do you have one in your car?
Have what?
Catalyst in your car?
Gas.
No, gas in it. It's underneath your car next to the muffler. Catalytic converter. That's why they call it a catalytic converter, because it has a catalyst in it. It has a precious metal, either platinum or palladium in there, which is why people steal them. That takes the unburned gas fumes and that aren't burned in your engine and burns them in there, which is why it gets very hot. If you've ever gone underneath a car, if you've driven for a while, that is really hot. It's easy to put a shield around it, so if you don't park over leaves, you don't set them on fire. Where else do you have catalysts? Closer. In you. Enzymes are catalysts. Without enzymes, we would move very slowly. Kind of like you're doing now. Okay. So there's a solid phase catalyst. What it does, remember we talked about orientation. In this case, it grabs the reactants and lines them up in the correct orientation. That's what an enzyme does. And we call them, instead of reactants, biology people call them substrates. So, here we go. Let's take